Good morning, everyone. So today we will start with the carrier-aided protection of the transmission line. What is the main aim of the electrical power system? The main aim of the electrical power system is to maintain the uninterrupted supply of the electricity to the consumers. So electric faults, however, cause the interruption to the supply, and when a fault takes place, it is detected by the protective relay and the fault current is interrupted by the circuit breaker. Now, the maintenance personnel must then rush to the fault location, rectify the fault, and restore the supply. So this actually applies to this concept applies to the this permanent fault. This concept applies to the permanent fault. In the permanent fault, the electrical faults cause the interruption to the supply, and when the fault takes place, it is detected by the protective relay and the protective current is interrupted by the circuit breaker, and the maintenance personnel must then rush to the fault location to rectify the fault and restore the supply. So however, as we have also discussed, there is the statistical evidence that about 80% of the faults are not permanent but are the transient faults, and these faults are actually caused by the breakdown of the air surrounding the insulator, and these faults disappear by themselves if the supply is briefly interrupted and the arc path is allowed to deionize. Now, as we have discussed, that there is a statistical evidence that about 80% of the faults in the power system are the transient faults and are not permanent but are transient, and faults are caused by the breakdown of the breakdown of the air surrounding the insulation. So this fault is caused by the breakdown of air surrounding the insulator. So it is caused by the breakdown of the air surrounding insulator, and these faults actually disappear by themselves if the supply is briefly interrupted and the arc path is deionized. Now, whenever the fault takes place, we can tentatively assume that the transient fault has interrupted the supply, and then we wait for a short while before switching on the circuit breaker, and this is known as the recloser. And this recloser can be carried out manually or automatically. Recloser, this is known as the recloser. So this recloser can be carried out manually or automatically, and if the fault was indeed a transient one and interruption was of the duration greater than the deionization time, then the recloser would be successful. That is, there would be no reoccurrence of the fault. And now the some of the typical deionization times of various system voltages is given here. Like we will have for 66 we will have 0.1 second. Then for 132 kV we will have 0.17 seconds. For 220 kV we will have 0.28 seconds, and 400 kV we will have 0.50 seconds. Now, if the fault is permanent one, recloser will be unsuccessful. So in case of the permanent fault, this recloser would be unsuccessful. So we will have the unsuccessful recloser if the fault is permanent. Unsuccessful recloser if the fault is permanent. That is, the protective relay will immediately cause the circuit breaker to trip. So circuit breaker will trip in that very case because the relay will sense that. So thus, in case of transient fault, recloser help in keeping the downtime to minimum and in increasing the availability of the supply. So in case of the transient fault, what the recloser is doing? The recloser helps in keeping the downtime to minimum. It helps in keeping the downtime to minimum. It helps in keeping downtime to minimum. Keeping downtime to minimum and increasing the availability of the spray. The recloser has different implication on low voltage and high voltage and extra high voltage systems. Now, as we have discussed in a low and the medium voltage systems. Now in the low and the medium voltage systems, in the low voltage and the medium voltage systems, we will have the maximum of 3 consecutive reclosers are allowed. So maximum of the 3 consecutive 3 consecutive reclosers are allowed, and if the fault persists even after the third recloser and even when the third recloser fails, the circuit breaker is logged out and no more reclosers are allowed. The multiple reclosers in the low voltage and the medium voltage systems helps in burning out the object responsible for the fault, say a tree or branch, thus helps in clearing out the fault. Only one recloser is allowed in the in this extra high voltage system. In the high voltage and the extra high voltage system, only the one recloser is allowed, and if done sufficiently fast, it helps in improving the stability of the system. So this recloser, if done fast, it helps in improving the stability of the system. Helps in improving the stability of the system. This is so because as soon as there is interruption in the system, the rotor angle of various generators starts drifting apart. So when the interruption is there in the system, so the rotor angles of various generators, the rotor angles of the various generators start drifting apart, and if they drift apart beyond the critical angle, the system loses the stability. However, if you see the supply is restored before the critical time elapses, the system can pull together and it will remain stable. Now, since the high voltage and extra high voltage lines are generally the tie lines, there is the presence of the source at both the ends. So in order for the transient fault arc to be quickly quenched, the line must be instantaneously and simultaneously tripped from both the ends before a recloser can be attempted. So this thing must be taken into consideration. That is, in case of the high voltage and extra high voltage lines, these are actually the generally the tie lines. These are generally the tie lines, and there is the presence of source at both the ends. We will have the source at both the ends, and in order for the transient fault arc to be quickly quenched, the line must be instantaneously and simultaneously tripped from the both ends before the recloser can be attempted. As we have discussed about the 3-step distance protection for the entire line length, it does not meet the requirement of the instantaneous and simultaneous tripping from both the ends that we have discussed in the previous modules. So in the previous modules, as we have seen that only 60% of the length of the line, here you will see only the 60% of the length of the line, 60% of the length of the line, this one, of the length of the line in the middle of the line gets high speed protection from both ends. For about 20% of the length of the line near each end of the line, that is total 40% of the line length, the protection is instantaneous is instantaneous from the local end but is delayed from the load end. So this is explained in this figure, as we have also discussed in the previous chapter. That is 60% protection is given. However, it is the protection is instantaneous for 20% of the line. It is instantaneous from the local end but delayed for the remote end. So in order to be able to implement the auto recloser, we need to augment the distance protection so that instantaneous stripping from both the ends for 100% of the line become possible. So what is the way out? We must augment the distance protection so that we must augment the distance protection. So what we have to do, we must augment the distance protection. We must augment the distance protection so that instantaneous stripping from both the ends for 100% of the line become possible. So that instantaneous stripping from the instantaneous stripping from both the ends for 100% of the line length become possible. And this can be actually achieved by carrier-based scheme. This is achieved by the carrier-based scheme. This is achieved by the carrier-based schemes. Now the various options for the carrier. Now the protective relay process the information contained in the voltage and the current at the local end. So it will process the information which is contained in the voltage and the current at the local end. The relay only indirectly infers about the condition at the remote end, though through these signals. As the fault distance increases, the picture can be more and more fuzzy. As the fault distance increases, as this distance is increasing, so the picture becomes more and more fuzzy. Hence, there is always an ambiguity about the exact location of the remote fault, and it becomes impossible to distinguish between the fault just beyond the remote bus and one just ahead of it. However, there is no ambiguity about same fault from the end near to the fault from the end which is near to the fault, because as the fault moves just beyond the bus to just ahead of it, from this to this, as the fault moves, there is a 180 degree change in phase of the current at the nearest end. Thus the nearest end has a clear-cut information which is so difficult to extract using the power, frequency, current and voltage at the remote end. Now, if we could somehow pass on this small amount of information from one end to the another, suppose from this end to this end, then in that very case it would enhance the quality of the decision making at both the ends. We therefore need some carrier. To carry the information. Various attributes of ideal carrier what are the different attributes of an ideal carrier is? that is delay involved in communication should be small. So the communication delay should be small. It should be less compared to the time period of the system frequency. At 50 Hertz, the delay should be much less than 20 milliseconds. At 50 Hertz, the delay should be much less than 20 milliseconds. That is, the communication delay should be small compared to the time period of system frequency. Should be less than compared to time period of system frequency. Now, since only a small amount of information is to be passed, the carrier channel need not have very high bandwidth for the protection purposes. So, no need of high bandwidth. Now, faults on a power system should not adversely affect the functioning of the carrier channel. Now, the faults will not affect the carrier channel. Now then we will have the carrier channel should be under full control of the utility company. Carrier channel controlled by the utility company. And now the carrier equipment such as carrier transmitter and receiver should be protected from a high potential of the EHV line. So carrier equipment protected from high potential of EHV line, and it should be also economical. Now the last is it should be economical. The carrier channel should be economical. So these are actually the attributes of an ideal carrier channel. Now, table here shows the various carriers, options for the carrier signal along with their salient features. So, here shows the option for the carrier channel and their salient features. Now, in this case, you will see first is the leased telephone line from the telephone service provider. First one. Now, in that very case, the problem is that the running cost is very high, maintenance is a problem, and the guarantee of the quality of the service may be difficult to obtain. Second one is terrestrial microwave communication channel, either owned by the utility or leased. So in this case, the problem is that the frequency range is between 3 to 30 gigahertz. The range of communication is the line of the site. A large number of antenna towers are required because we will have the line of sight communication is there in that very case. Therefore, initial investment and maintenance costs are both very high. It provides a very large bandwidth which may be shared with the other data communication services. Now, satellite communication via Vset terminals using geostationary satellite at 36,000 kilometers. The frequency range is in this case is between 3 and 30 gigahertz. Propagation delays involved are of the order of 2 into 36,000 kilometer. That is 240 milliseconds. That is 12 cycles, and this is not permissible for real-time power system protection. Large bandwidth is available in that very case. However, the power line carrier communication. It is actually the most economical since the power line conductor doubles as physical medium for carrying the carrier signal. The carrier signal is the signal of much higher frequency compared to the power frequency which is coupled to the EHV line. Frequency band allocated to this surface is 50 to 200 kilohertz. Thus, the carrier signal frequency is just above the audible frequency range and below the medium wave radio broadcast band. Due to the moderately low frequency of the carrier, a small bandwidth is available. However, protective relaying does not need a large bandwidth. What is important is the delay involved, which is very small in case of power line carrier. That is, for a 1000 kilometer line, it will cause a delay of 0.33 milliseconds. So it is most economical power line carrier communication. And the carrier signal is a signal of much higher frequency compared to the power frequency, and it is actually coupled with the EHV line. And the frequency band in this case is allocated is 50 to 200 kilohertz, and the carrier signal is just above the, which is above the audible frequency and below the medium wave, that is MW radio broadcast band. And also it has the small bandwidth because for the protection large bandwidth is not required. So, and delay involved is very small in that very case. So that is very important part. Now coupling and trapping the carrier into the desired line section. As you already know that the power transmission line, line operates at a very high voltage. So power transmission line, the voltage is very high in that very case. It is of the order of hundreds of the kilovolts, and the carrier signaling equipment, if you see the carrier signaling equipment, that is the carrier current transmitter and the current carrier current receiver, operate at the much low voltage. Now, therefore, we need a method of coupling the two so that neither the high voltage line gets shorted through the carrier equipment, and nor does the signaling equipment get damaged due to the extra high voltage. So we can have a system in such a way that this transmission line would not be shorted, and it would not be shorted because of this carrier equipment and signaling equipment. This carrier equipment does not get damaged due to the high voltage. So the damage should not be there due to the high voltage. So here in this figure it shows one of the arrangement for coupling the carrier on the line to ground basis. Now in this case you will see the line traps are actually there which confine the carrier signal into the desired line. These line traps are there. It has it keeps the carrier signal into the desired line section in this case. Now let us analyze this figure. Now in this case we will have this coupling capacitor, that is this one coupling capacitor. It forms a we will have here the coupling capacitor. Now we will see from this that the impedance of this coupling capacitor is very large at the 50 hertz. So impedance ZS is very large at 50 hertz compared to that of the parallel tuned circuit, that is LP and CP. So which is tuned to the carrier frequency. Now the coupling capacitor drops most of the 50 hertz voltage so that a very small 50 hertz voltage appears across the signaling equipment. The series circuit, that is CS and LS, is designed to resonate at the carrier frequency. Since the impedance of the series circuit is ideally 0, it ideally zero, it provides a very good coupling at the carrier frequency. So since the impedance of this Zs is ideally zero, it is ideally zero, so it provides a very good coupling at the carrier frequency. Now, the parallel circuit consists of L, P and Cp as shown here, is tuned to resonate at the carrier frequency. Since the impedance of the parallel resonant circuit is ideally infinite, so the impedance is ideally infinite, so this is, let it be Zp, it is ideally infinite. In that very case, is ideally infinite at the resonant frequency, so it develops the maximum voltage at the carrier frequency. So it develops the maximum voltage at carrier frequency and helps to extract the maximum carrier signal. The series and parallel LC tuned circuit, that is this one and this one, helps in efficiently coupling the carrier into this EHV line. The carrier signal, however, needs to be confined to the designed line section. So for that, we will have the two line traps which are parallelly tuned LC circuits. In that very case, you will see these two line traps, which are LC circuits, resonate at the carrier frequency, and it prevents the carrier signal from spreading into the rest of the transmission system by virtue of the extremely high impedance at the carrier frequency, because it provides a high impedance at the carrier frequency. The line traps, these line traps are so designed that they do not offer any significant impedance at 50 Hertz, that is the power frequency, which is not required. The line ends are thus clearly demarcated as far as the carrier signal is concerned, and the clear-cut demarcation between these, it actually helps in establishing a well-defined zone whose actually boundaries are crisply defined, and which is good for the protection system.